In this example, we're going to look at this rational function given through the lens of calculus using limits to get information about roots, discontinuities, and horizontal and vertical asymptotes. So here, the rational function that's given is already given in factored form. It's x plus 1 times x minus 2 on the top, and then on the bottom it's x minus 2 times x plus 2. So we see right away that there's a factor x minus 2 that appears on the top and on the bottom. And so we could start by reducing this factor out, leaving us with x plus 1 on the top and x plus 2 on the bottom. Now, that equal sign does not make sense unless we specify the single x value that canceled, or that when we canceled out the factor, no longer would be a division by 0. So since we canceled out the factor x minus 2, we have to keep the fact that we still cannot plug in 2 to the reduced rational function, because that would have given us a 0 in the denominator for the original unreduced rational function. So actually, since we're in that realm of thinking, that x equals 2 value is actually going to be a whole. And so let's go ahead and jump over here to the information about discontinuities looking at a whole. Since we reduced out that factor x minus 2, the root that goes along with it for the bottom is where we're going to have a whole. So we have a whole at x equals 2. And the limit information we can do to justify this, or to figure out exactly where that whole is located, would be looking at the limit as x approaches 2 of the original function. See, now we know right away that if we were to plug in 2 to the original unreduced rational function there, we would have gotten a 0 over 0. But we can use the cancellation property that tells us that the limit of the original function would be equal to the limit of that reduced fraction. And so we can look now at the reduced fraction and compute that limit by plugging in. So when we plug in, we drop the limit notation in front, so we'd have 2 plus 1 on the top and 2 plus 2 in the bottom, giving us that limit value of 3/4. And so notice that that's telling me really where this whole is going to be, but realize that we're really justifying that it's a whole because that limit exists, but the function value does not. Because had we plugged in 2 at the beginning, we would have gotten the 2 plus 1 times 2 minus 2 on top, and then on bottom the 2 minus 2 times 2 plus 2, and that would have ultimately given us 0 over 0, which is undefined. Okay, so what we're saying here is 2 is not in the domain, but that limit does exist as x approaches 2 for the function, so that's the full justification for the whole. Alright, so now let's take a step back here and look at roots. For roots, we can look at the reduced fraction, the reduced rational expression there, because we've already only just reduced out the whole, and we've already taken care of the whole. So roots would be wherever the top is going to be equal to 0. And so when we look at the top, that top is x plus 1, so we get the root then for wherever that would be equal to 0. So that root's going to happen at well, I'll go ahead and write it out. X plus 1 is equal to 0 is where I'm looking to get the root. The top equal to 0 would be where the fraction's equal to 0. And that gives me the root x equals -1. Now, we can justify that this is a root by looking at the function value, as well as we can identify the limit here. So look here at the limit as x approaches -1 of the original function. We can go straight to the reduced form to make our calculations easier. And we can compute that limit by plugging in. So we'd have -1 plus 1 on top and -1 plus 2 on the bottom. So we do have a 0 over 1, which is 0. We can also see that f of -1, if we were to have plugged it into the original fraction before we reduced, we would have still gotten that same value there. So we will plug in the negative 1 to the unreduced form to get the function value. And what we would get still is that 0 on the top. And the other factors around are not 0, both on the top and the bottom. So we have a 0 times negative 3 on top, which is just a 0 on top. On the bottom, we would have the negative 3 times the 1, so negative 3 on bottom, but 0 over anything non-zero is in fact 0. So notice here that these two things combined, the fact that they're both equal to each other, is really telling us that the function is continuous at the 0, x equals negative 1. So not only does the function value is equal to 0 there, it's nice and continuous there as well. Okay? So far we have taken care of the roots, we've taken care of one type of discontinuity, but we have one more type of discontinuity to handle, and that would be the vertical asymptote. So let's look here at the vertical asymptote. We are able to get the vertical asymptote by looking at the reduced form and figuring out wherever the denominator is still equal to 0 after we've reduced out any of the wholes, really. So we get that by setting that bottom equal to 0. So that would be your x plus 2 is equal to 0. So that gives us x equals negative 2 being our vertical asymptote. And we can justify that by looking at limits. Now, vertical asymptotes in general, if we were to just try to plug this in, look what happens. We've got the limit as x goes to the negative 2, the one that we know is going to be a vertical asymptote, of the original function. We could look at that and we could put that directly into the reduced form. So that would be the x plus 1 over the x plus 2. When we were to plug that in, we'd have the negative 2 plus the 1 over negative 2 plus 2. So notice that we have a negative 1 over 0. Now, that alone doesn't tell us anything. This is telling us that we have to go to the one-sided limits, because we're dividing by 0 here, and we don't know which sign 0 ate. That's the way I like to think about it. 0 doesn't have a plus or a minus sign with it, but we really need to know individually when we're coming in from the left and coming in from the right whether that 0 is coming in from slightly below 0 in the negative realm or slightly above 0 in the positive realm. But what this is telling us is knowing that we have a non-zero constant over 0, what that's telling me is that right away I know each one of the one-sided limits is going to be either plus or minus infinity. I just need to figure out which one. So anytime you get this non-zero over 0, you've got to go to one-sided limits. So non-zero over 0 is telling you to go to one-sided limits. And it's going to give you, for each one of these, plus or minus infinity will be the answer. Okay, because dividing by 0 would be blowing up the whole fraction to either plus or minus infinity, and we just need to know which sign. So that's the general approach for any time you get a non-zero over 0. So let's look at these one-sided limits. We've got the limit as x approaches negative 2 from the negative side of the function. And we've got the limit as x approaches negative 2 from the positive side of the function. We've got to figure out these individually. So let's do this. We can look at the reduced form. And so that reduced form there is your x plus 1 over your x plus 2. So this one-sided limit here is really just to identify what's happening in the bottom. We know the top is going to be this negative 1 in both cases. So now we just need to know whether to attach a plus sign or a minus sign with the 0. So here in the bottom, we would have a negative 2 minus. So we'd be talking about something slightly less than negative 2. So you might want to think like negative 2.1 in your head. So negative 2 minus, and then adding up 2 keeps us into the negative realm of things. So maybe I'll go ahead and write that. And let's go negative 2 minus, and then we're going to add 2 to it. And then for the other one, it would be the negative 2 plus, and we're going to add 2 to it. So we're looking at negative 1 on the top for each one. The negative 2 minus would be like negative 2.1. Add 2 to it, we're still in the negatives, so it would be a 0 minus. And then if we're talking about negative 2 plus, we're talking about slightly bigger than negative 2, so maybe like a negative 1.9 in our mind. So negative 1.9, adding a full 2 will keep us in the positive realm of things. So that would be a 0 with a little plus sign thrown to it. So that little sign that's attached to the 0 is telling us which sign 0,8. And we're going to be able to utilize that sign to help us determine which of the two infinities we're looking at, positive infinity or negative infinity. So for the top one, we have a negative 1 over 0 with a negative attached to it. So the top is negative, the bottom is negative. So overall, the whole thing is going to have to be positive. So that tells us it's a positive sign that we're attaching to the infinity that we knew we were going to get. On the bottom one here, we've got a negative 1 on top, and then we've got a plus sign attached to the 0. So we've got a negative over a positive. Well, a negative over a positive would be negative, so it's the negative sign that we're attaching to the infinity there. Okay. So that tells us right away our behavior at the vertical asymptote. It's telling us to the left of the vertical asymptote, we are going up forever to positive infinity. And to the right of the vertical asymptote, we're going down forever to the negative infinity. Okay. So the very last thing that we need to figure out here is horizontal asymptote for this rational function. So we get the horizontal asymptote by looking at the ratios really of the leading coefficient, because the highest power on the top matches the highest power on the bottom. And so neither one is overtaking the other. The bottom's not dominating, the top's not dominating. They're going hand in hand. And so it's that ratio of the leading coefficients that gets us our horizontal asymptote. So here we see a 1 times x on the top and a 1 times x on the bottom. So the 1 over 1 would give us just the y equals 1 for our horizontal asymptote. And we can get that justified using calculus, looking at the limit as x goes to negative infinity of the function. We can look at the reduced expression, and so that would be the x plus 1 over the x plus 2. And this is where the highest power term is dominating for limits as we go to infinity. So we're looking really at an x over x situation. The x over x is going to reduce out to just a 1, so that's where we're getting the limit as x goes to negative infinity of just 1. A constant there is just going to be 1. So that does show you that as we go out to negative infinity for the x's, we are approaching that horizontal asymptote. And the exact same thing's going to happen here for the right-hand side, where we've got the limit as x goes to positive infinity of the function. That'd be the right-hand side of the graph. Again, we look at the reduced form, and again, we have that highest powers dominate here for the rational function, and so we'd be looking simply at x over x, which reduces out to 1. That is telling you that it reduces out to 1, so that's where we're getting this idea that the ratio of the coefficients is telling us where to go. That ratio of the coefficients is 1 in this case. So we do, in fact, have that limit that we expected. So this example was showing us, using the lens of calculus, all those things that we have been learning about rational functions, even starting in algebra and pre-calculus.